Okay, so maybe a very brief summary of yesterday. So yesterday we were talking that we can really understand generalized entropies in terms of Boltzmann entropy. So for a long time there has been this discussion whether we require generalized entropy functionals, which are not of the Shannon type. And what we can easily see is that if we apply the Boltzmann entropy prescription outside of the class of IID processes, that Boltzmann entropy automatically produces such non-Shannonian functionals, and that this is actually a natural feature of the game, and that Shannon entropy in particular, so the Shannon-Gibbs entropy, is a consequence of Boltzmann entropy being applied to IID systems. So that was part one. Part two, we showed we discussed that for not for a reasonably large group of family of processes, it may be in principle possible to map this process to another process. So basically to write the text not in terms of the original Latin alphabet, for instance, but in terms of maybe numbers that pick out words in a lexicon, or just in terms of words rather than of letters. And this is something that Shannon will do if you code these things in terms of the alphabet or in terms of the lexicon. The entropy is much smaller, so we can capture much more of the correlations if we choose to represent data streams not in terms of the alphabet, but in terms of chunks of paths. And therefore, we can actually do the thing that we can map a process that contains correlations to a process that is very close to IID, or maybe IID process. If that doesn't work, one still can map to Markov processes, in both cases we have the right entropy in place to measure the information production. In the IID case, the Shannon entropy; in the Markov case, the conditional entropy. So what happened then is, so we map the process to the IID process, measure it with the Shannon, the information production with Shannon entropy there, normalize correctly the units of information, so that we still get the result in bits per emitted symbol of the original process. Now, whenever we look at do something like statistical physics, then there's something behind this, which is called it's the so-called concentration of measure phenomenon, which gives rise to a number of sometimes slightly unintuitive findings. So, for instance, if you look at hyperboles and you randomly toss in points, so you sample randomly points within the hypersphere, then so actually within a hyperbole, so then actually you can take any epsilon you want, and as n goes to infinity, the probability that all your samples are within an epsilon distance from the surface of the hyposphere goes to 1. So this is, for instance, one of the results of consequences of concentration of measure phenomena. So which comes down to the observation that for very large hypospheres the surface basically is equivalent to the volume, and
sorry, the statement is as n goes to infinity, you can make epsilon as small as you want.
You take any epsilon you want.
Okay.
So it's like in the weak formulation of the central limit of the law of large numbers.
Okay.
Where you also have different ways to. So yeah. So you take the sphere, you take a epsilon distance, a shell in the surface, and then you let n go to infinity.
Yeah.
Then this epsilon region, as n goes to infinity, contains almost all of the volume. So that's funny thing. Okay, but the concentration of measure already happens in the classical max-n principle. So basically, we have a Gaussian distribution function that concentrates as n goes to infinity. So this nice thing. We have the Gaussian, and the sigma goes with square root n, and you normalize with n, so this x, then one can see actually that the diameter actually goes like 1 over square root. The relative error goes to 0. So even though if this is the histogram K concentrated around some A1. So if you have a Gaussian located around your extremal around the histogram that maximizes that has maximal probability, so here you have the maximizer. Then if you look at P, which would be K divided by the number of observations, then you get this, then you get actually that P is becomes exactly located as n goes to infinity at the point, one particular point which is characterized in, again, maximizer. So if that were not the case, then max n would not work. And there's a general way of thinking about that, and that is something we will very briefly discuss. And so yesterday we looked at this triangle, and today we will look at how typicality factors into this game. And that would be the condition. So again, I would like also to remind we are talking about paths now and not about states. So the difference is if we have correlation in the data, we don't make dies where we draw all the possible states on the die and throw the die, this die. We take a much larger die where on each base of the die, we actually draw one particular realization of the path. And that's what we sample, because at that level, we can still, again, can treat the paths as independent from each other.
It would be like sampling the entire
Yes.
bettings of a roulette player, a single bet.
Yeah. So you directly sample your entire path, in which case you can, these paths may have memory, they may depend in complicated ways on their past. And it doesn't matter. Once you just look at paths in total, then you can again think of these paths as being independent from one another. Okay, so how do we characterize such paths? So again, we would have a random variable that samples t time steps of the path. That would be big xt. And now we say the following. So we look at categorical processes. So that's actually all we usually need. In particular, as our universe is probably very large but finite, so we have probably a finite number of elementary particles swarming around in the universe. So if we just can locate every particle up to a Planck length, also a rational number would suffice to code every position. So in the end, we probably could write principle right down. I don't see any particular needs for anything more than categorical processes to understand natural phenomena.
What are those?
With discrete and finite
Okay.
sample spaces, and unbounded. So the sample spaces may grow unboundedly, but at each time step they are finite. And that's exactly what we are looking at. So we are looking at not even at processes that necessarily sample each of the steps from the same sample space, which is, for instance, something that we need to understand evolution, because evolutionary trajectories show that we always build on stuff that has been produced earlier. So new states are actually invented time and again. A new genome sequence is sampled by mutation and gets fixated or not. So evolutionary processes are typically processes where the sample space does not remain invariant over time, and typically it grows. So if you look at the sample space of what a human society could do 10,000 years ago, and you look at the sample space of what a human society can do today, then there's definitely something like an exponential growth of possibilities underlying this process. So basically, it doesn't make sense to have a cell phone in a sample space of a Neolithic to describe a Neolithic society. It's simply not yet part of the system. Okay, so still we may have a complicated growing, shrinking, whatever sample space, and we assume now that on top of looking at categorical processes of that kind, there exist two functions that are monotonically increasing and lambda typically concave, sorry, then lambda, as you may as L indicates, is a generalization, should be a generalization of the logarithm. So it also doesn't hurt to assume the properties that lambda at 1 is 0 and lambda prime at 1 is 1, even though the latter is not really necessary. But can be practical. So then if we have two such functions, a monotonically growing lambda and a monotonically growing g, and we have that the quotient of these two things. So we look at the probability of paths up to time t. So at a path segment that is t time steps long, divided by the g of t, and then take the limit t to infinity. If this goes to 1 in probability, so meaning that for almost all sequences x of t, this sequence goes to 1. So the relative frequency of paths for which this is not true goes to 0 as t goes to infinity. That's the condition, and that is somewhat reminiscent of this here. And if this condition holds, yeah.
What is G? How is it defined?
Not yet.
Some function.
Yeah. You can take any two monotonic increasing functions. Lambda should be concave too. So that's it. You have a process, and now assume you can find two such functions, such that this is true for the process. If you can find such two functions, then we call this process compact. Why did we call it compact? Because in functional analysis, you have compact operators, which are the limit of finite size operators, and since our sample spaces are always finite but may grow unbounded, that was somehow where we lent the name from.
What is P here?
Hmm?
What's P?
The probability. So what yesterday we called G, but we called it G yesterday because we didn't indicate a particular sequence, but any sequence with a that has a histogram K, and therefore we called it big G. Simply.
So that's why you say it is finite state.
Yeah.
But
yeah, I mean,
otherwise it would be like 0, maybe something like this.
Exactly. So that's something I did not say. We usually in the paper we did a little bit more care. So we operated out all the sequences that really go to 0. There's one big difference that I would like to point out between if you look at states of a multi-component system, or if you like a spin system, or if you look at the time series of spins. Much of the math is similar, but there's one marked difference, and that is that if you have a particular spin sequence as a state and you add an additional spin, then it's not a priori guaranteed that the probability of the extended system, of the extended state, is smaller than the state before. For a process, we can with absolute necessity that the probability of a path is non-increasing. It may stay. So meaning that whenever the path separates into two possibilities, then if this is P and this P prime, then P it would be P prime plus P prime. So they only can go down. So the only possibility for the path here not to have decreasing, monotonically decreasing probability is that you have one step where you actually have no choice. So you just have one deterministic path to follow. In that case, the probability would flatten out, which also tells us that these probabilities always converge. Whereas in a system where I look at only at the total state, the state as a make it larger and larger could fluctuate in probability. So it may have I only know the German word Häufungspunkte, but it points where in some region the system arrives infinitely often, but it doesn't need not converge.
So why are we defining one over the probability of the why are we defining one over the probability of the path?
Why the reason is one could do it a little bit differently. So, but basically because if we have Shannon entropy, we usually write minus pi log pi.
Yeah.
But alternatively, we could write it sum over pi log 1 over pi.
I see.
And then so it's a if you go to generalized logarithm, actually this has been used to define what has been called the dual logarithm. So this would be if you have some generalized logarithm lambda x, so a monotonic concave function with lambda 1 is 0 and lambda prime 1 being 1, then the dual logarithm would be minus lambda 1. So you can have a function with this similar properties. And this plays a role if you, for instance, change your constraints from linear constraints to so-called escort constraints, then you get the same distribution function if you exchange the logarithm with the dual logarithm. So that there's some invariance there, which I don't know if we fully understand it. We know that this invariance exists, but well, let's leave that aside. However, now let's have this. Assume we are looking at processes where this is true. Then this basically is identical to the first line. So we said that the sequence, the random variable. So here we wrote it with the random variable and said, okay, convergence is meant in probability, and this can be translated into the first line. So now the little x are actually all the particular possible realizations of paths in the sample space up to time t. So we sum over all these possibilities with the respective probability p of x, and then this expectation value should go to 1. So, however, now that we know that this thing converges, and now we have no probability anymore, we don't have to say now this thing converges in probability. Now we have simple Cauchy convergence. I mean, this represents an expectation value, but there's no explicit random variable there anymore. So we can really take this as a function with the function of p actually, and then we take the limit t infinity and should go to 1. And since it goes to 1, since we say, okay, this converges, we can do the epsilontics and say, okay, we can localize now this convergence. So two functions need to exist. A function epsilon and delta, we call it here, which both go monotonically to 0 from above. And now we can define a upper limit and a lower limit for the probabilities that we accept, and say, okay, we define now this set A of epsilon t, so which would be all paths in the sample space where we can squeeze the probability p of x between those two limits, and this limit is basically this. Maybe I should use the blackboard here for one additional calculation. So we said lambda 1 over x divided by g of x goes to 1. So this basically means that this means that for epsilon there exists some t, so that for all t prime larger than t, we have then 1 minus epsilon is smaller than x, t smaller than plus epsilon, and we bring the g of t to the other side. And then we take the inverse function of lambda and I do it in one step and divide by 1 over p, then we have here this. Yeah, careful with the 1 over, because then I also have to exchange here the sign. So because by 1 over I have to swap the two sides. That's exactly what we do here, and this we have defined as the plus. This is minus.
Where do you get the first equation? So over there I see a summation, over there I just see two
This
terms.
one.
Yeah.
This one we assume to be true. So if we have a x, if you look at the path x, for which this convergence holds, then we know this from the convergence. So from Cauchy convergence, we can say.
So does this thing follow from the first equation on the board?
Yeah.
Because over there I still see a sum.
This
Oh, this one.
from this one,
Okay, sure.
which we assume which is true by assumption now at the moment, and which basically then means that for this set, this is true. So we can say the probability of sampling a path X that is not in this set goes to zero with, and we can squeeze it with this function delta.
So what's the function of the first equation here then?
Sorry?
What does the first equation do on the board?
The first equation, on
Yeah,
the
that
top,
one.
it just translates this equation into a language that where we don't have a random variable here anymore. Here we still have the big X, which is the random variable, which has no definite value. It just samples. So basically, this is what the first equation means in terms of how you would compute it. You sum over all realizations, possible realizations of the random variable X, which is the small x, take the probability and evaluate this. So this is simply the first equation written in a way that eliminates the random variable. Then we have Cauchy convergence, and then therefore we can localize the probabilities. And that is what we call now the typical set. And again, typicality is not the exact thing, because you could use now, you have some freedom in choosing your localizers. So you can have some freedom in choosing how your epsilon and the delta goes to, in particular, you have some choice about how your epsilon goes to zero. You can let epsilon go to zero more quickly or more slowly, which has an impact on, what a typical set is not uniquely defined. But whenever you have but you can choose any, so you have some freedom. And that many of these things here are not uniquely defined. It's not a bad thing. So I think in the Gaussian case, please don't beat me now if I'm wrong. I'm not sure now. Epsilon can be anything of t to the power minus alpha, with alpha, I think, larger than zero and smaller than 1/2. Or I'm not sure anymore, larger than 1/2 and smaller than 1. One of the two. So you have some freedom of choosing epsilon in such a way that this relation holds. So because all that you want is that asymptotically this set collects all those parties which, in terms of being observable, may be relevant. All other passes have basically a zero probability of being observed. And that's also why one calls it a typical set, because the number, so if you just count the number of paths, it may be that actually in terms of the counting measure, the size of so if we just would look at the cardinality of epsilon p divided by the cardinality of the entire sample space, this may or may not, this may go to zero. So in terms of the counting measure, the typical set may be very, very small, whilst in terms of the probability measure, it actually collects all parties that you would possibly observe with probability 1. So the probability of observing anything else goes to zero. So that's why it's called the typical set. In particular because of this, because now you have a huge sample space, but actually your typical set is again concentrating a very small point, which may be again large, but compared to the entire sample space, it's very, very small. Now, one can, now we have a typical set, but things are a little bit more. And if we would look only at IIT processes, we could already, we are almost done. We would almost be done, and we could almost directly construct a link to statistical physics. However, here we need a little bit more work. If we look at paths, because some mischief could happen, and one way to get rid of a little bit of mischief is to say the following about the process. We also want that this ratio between the upper and the lower probability here these ratios are defined. So P0 is actually without the epsilon, which would more or less be the estimate of what we typically would expect the probability of a path to be at step t. And then we take the ratio to the upper and the lower limit, and the ratio to the upper limit goes to infinity, and there should be a zero, a minus here, and the ratio of the lower limit goes to 0. That means that if we zoom in, if we take a lens and zoom in onto the probability distribution of paths, then it would probably look something like that. Here we would have 1, 0, which locates actually exactly those paths which have probability P0, and here P plus goes to infinity, and P minus goes to 0, which basically means we are looking at distribution functions of paths, which dynamically somehow use the whole possible range of values. You could, for instance, have another thing. If this would be more localized, like here, and is not spanning the whole thing, then we would say that the system is not filling. The other case we say it's filling. And if it's this one here, then one can show that for the function lambda, for the generalized logarithm, the following is true, that pick any positive small lambda, fix it, take z, take this quotient, take z to infinity, and you get 1. So that's a property that, for instance, is true for the usual logarithm. So if you have log lambda z divided by log z, we have here this is log z plus log lambda divided by log z, and the first part goes to 1, and the second part goes to 0, so this goes to 1. Yeah.
So I still have a question about this filling thing.
Yeah.
So if you divide by p plus, so p is a number between 0 and 1, right?
Mm-hmm.
So how can r plus ever be 0?
In the limit.
Which limit then?
T to infinity. When I have this arrow, I always mean as t goes to infinity. Also, I just don't always write limit t to infinity.
So I would say it would go to 1, not to 0.
on that side, there should be a minus. It's a typo, sorry.
Yeah, sure, but how can it go to 0, I wonder? So you have the statistical probability, and if you're like a bit above,
Because epsilon, how can it go to 0? That is simply because this epsilon is also not a constant, it's a function in t. And as gt grows and epsilon t shrinks, the product can yet grow or shrink. So you have
so P plus is always larger than P0. Agree?
yes, and p minus is always smaller than p0.
Yeah, so I wonder if you divide by P0 divided by P plus, this is always larger than 1.
Right.
So if you divide P0 by P plus,
Yeah.
this is always larger than.
This is always smaller than one, and the other one is always larger than 1. And the one smaller than 1 can go to 0, and the one larger than 1 can go to infinity.
Okay. I don't see it, but it's sure.
Wait, did I make it more possible? So what we are saying is that lambda minus 1 g 1 minus epsilon divided by lambda minus 1 g t. That this can go to 0. This is what you are doubting.
Yes.
Uh,
Yeah. So flipped, I guess. But yes.
It's doubly flipped because it's 1 over.
Oh, sure.
So it's 1 over 1 over. The point is that epsilon t, g of t, can get large. This does not mean, while epsilon alone usually gets small, epsilon times g can get large. If it would remain small, then you are right. Then this probably would go to.
Yeah. So I just had this.
This probably would go to
Sure.
1. The whole thing would concentrate at 1.
That was ideal.
Yeah, and but it need not be there. So you can. Actually, for all well-behaved processes, it's like that. So for all exponential processes, this is actually true. Yeah. So what we get from that is that this is true, then lambda has to has this property. This which basically means that lambda set has to be of this, has to grow at least as slowly as a power of a logarithm. And so this already shows us that lambda equal the logarithm is a very good choice first order, but it could also be, and as you see, it could be the logarithm to some power, but in fact, whenever you just take a power, you just you can transform both functions. So if you, for instance, have a log to the power dvg as a pair of functions that is viable, then also log g to the power 1 over d is a viable choice. So if you can choose this, then this is also true. So this choice of lambda and G need not be unique, and but they can be translated into one another. So they form equivalence classes. If you do something more brutal than a power, let's say you want to transform with an exponential function, then this is not equivalent. So if you would transform the lambda, the big lambda, with anything that grows more brutally than a power, then the other representation would not be equivalent. And that's why we have once looked at with a colleague, Jan Korber, at the asymptotic expansion of distribution functions, and we see that actually we end up with exactly such a family of equivalence classes, where each equivalence class is basically determined by these exponents, which are the scaling exponents then of the problem. And the typicality approach basically reproduces the structure of these equivalence classes. So they go together well with the scaling expansion approach, which will not go into here. Okay. So one thing one should note is that for the Zahles distribution for the Q exponential, so for the Q logarithm, where S values P minus some Pi log Q, Pi and log Q log Q of X. That would be 1 minus Q minus 1. So this is the limit Q to 1 goes to the so this is it's actually the trick that you use in replica theory, where you actually replace the logarithm in your partition function with a Q logarithm, then you can do all the computation and you take Q to 1. Here, this is basically the same thing. And if you take this as a logarithm, then you would have something like that. This is not a filling process. So processes that would have Q logarithms as their typical scale would not be filled. So this means that this Q logarithmic regime somehow works a little bit different than the other one, and that one should treat it on its own. Actually, and I just will mention it, it's in fact funny. So one has to treat typicality in the Zahles entropy regime a little bit differently than from the other regimes, but there's basically the following thing that one can roughly say is that if you define your typical set via the usual entropy, so basically with the usual logarithm, then you get the typical set. If you do it not via the entropy but via the free energy, then it's the Renyi entropy that defines the typical set. And if you look at the partition function, then, so if you define typicality via the partition function, then it would be Thales entropy that describes the problem. So in fact, somehow Thales entropy is more closely related. So we could say Thales entropy is actually related to the partition function. It's somehow a representative. One could interpret it as a representation of the partition function of a system. Okay. The scaling expansion we were talking about, which was producing this kind of logarithms, can actually be obtained from the axiomatic approach to defining Shannon entropy. So there are 4 axioms that uniquely define Shannon entropy of all possible information measures up to a multiplicative constant, which is the Boltzmann constant, so the unit of information. And if you drop the composition rule, then one can show that all the resulting entropies would have instead of the logarithm, a generalized logarithm that basically is of this form. This is what one can prove. So the first 3 Shannon-Khinchin axioms do not uniquely define the function, but they define equivalence classes of function. Good. Yeah. Good. So now one can do the following. We can define an entropy function, or simply define it, and simply replace now. It's a path entropy. We did not normalize it, so the units of information should still be adapted, but for our purposes here, this is not necessary. So we say now, okay, the entropy measure of the set C, where C is again subset of the sample space, is simply the sum over the path is in C, and you take the expectation value over the subset of lambda of 1 over px. So this is how we define lambda entropy. And then we see we would like to relate this lambda entropy to, we would like to compare this lambda entropy on the typical set with the lambda entropy on the entire sample space. And intuitively, we would like, as we say, okay, almost all paths, all relevant paths are in the sample in the typical set, and therefore one should believe that this holds. This always holds. That the limit of the lambda entropy divided by the of the typical set divided by the lambda entropy of the entire sample space should go to 1. This, however, turns out not to be true. So we need to again set it as an axiom and say, okay, we call processes simple if this holds. And in fact, that's also something that's not yet completely out, but we already have the proof, is that as long as your sample space is not growing faster than any stretched exponential, then all your processes are simple. So if your sample space grows like n factorial instead of 2 to the power n, 2 to the power n would be the usual thing. And the spin or some w to the power n, I have some object with w states, and then add other ones, and with each one I multiply the number of possibilities by W, so we would have exponential growth is that of sample spaces would be the usual thing, but there is plenty of processes that we can look at where the sample spaces grow super exponentially, like n to the power n or like n factorial, and those are still all well behaved, so that we can prove. So all these processes are simple. Only once you go to sample spaces that are really brutally growing, like e to the power a t to the power alpha, so any stretched double exponential function. So if you have a sample space that grows like a double exponential function, then you could go into trouble. Then you have to check this condition, whether it holds or not. This does not tell you that you could not have a process on a double exponentially growing sample space, which is still simple. All we say is that you can construct processes for double exponentially growing functions, which are not simple, which violate this condition, which is somehow brutal because it tells us that this condition simply tells you that the entropy measure is continuous with respect to the probability measure, and for this non-simple, if a process is not simple, the relation between the entropy, so that would be singular. So you would get a non-zero contribution of entropy from that part of phase space that has zero probability of being observed. So that's the simplicity condition. So again, for most of the processes that we would typically observe in natural circumstances, they are simple. And if they are simple, then one can also prove the following things. One can prove that the lambda entropy in the limit t to infinity divided by g of t goes to 1. So that's a nice thing. And then we can prove one more thing, and that is that the lambda entropy, so that lambda of the size of the typical set. So this is now again the cardinality of the typical set divided asymptotically behaves in the same way as this lambda entropy. So that basically tells us that we can estimate the entropy of the system by taking the logarithm of the typical set. So in the most of the cases that we're interested in, lambda would be logarithm, which basically tells us again the entropy is the logarithm of the size of the typical set, and this exactly again looks like Boltzmann entropy. So, but instead of looking at the total number of possibilities, so Boltzmann entropy for equidistribution simply reads S is what we already had, log multiplicity. So what we are saying here is that the size of the typical set basically estimates. That's why we said also this factorization of the histogram probability that we were talking about yesterday into a multiplicity and a sequence probability that where the sequence probability does not in particular depend on the order in which we it also again only depends on the histogram of the path, not the particular sequence in which it was sampled. This sequence was sampled. Basically tells us that asymptotically all these systems behave like a a system with multiplicity size typical set, and then a sequence probability, which would be estimated by this, how we have it, by P0. So so we get something like a equipartition property. And what we are actually saying is, in fact, the probability of all the sequences do not become equiprobable. So they can, because we see it's filling, they can still vary in a very broad sense, but still they will concentrate around this optimum. So in this sense, you are probably right that for most of the cases, that we are looking at, this limit goes to 1. But what we are saying is that for the extreme cases, at the very borders of a typical set, we can find sequences where it goes to 0, and where it goes to infinity. Yeah, with this quotient where you wonder if this was true. Or was it you?
I think it was you.
Yeah, sorry. Yeah. Okay. Yeah. So basically, the approach through typicality allows us to say, okay, well, in fact, we can approximate this process by another process which has a multiplicity size typical set and a sequence probability which is basically the average, the mean probability of sequences within this set. And the error you make by doing so goes to 0. That is again what this basically tells us, which is a nice thing, because we saw yesterday that making exact inference to perform an exact inference on some data streams can be extremely hard to impossible to do. Estimating the size of the typical set is something one can do. And even there, you sometimes have to invest a lot of work to achieve it, but sometimes you can actually do it explicitly. And here we have now 2 examples. Example 1 would be simply IIT processes, and we don't go really here into I don't go into details here. What we can do here is we could, for instance, find, if we choose in the IIT case, the obvious representative for lambda using the usual logarithm. If you there use the typical the logarithm, then we can, for instance, show that one has to use t times the Shannon entropy of the sampling distribution function for g of t. So g of t is a linearly growing function in that case, which basically tells us that all these IIT systems are extensive. So in the sense that the entropy simply grows with time. You have constant entropy production. So G of t is basically the accumulated entropy over time, or no, actually, if we would have to say, okay, G of t is the entropy entropy measure, and 1 over t G of t would be the entropy per emitted symbol, basically. And now we can look at the different process. So this is the usual setting. Everything's fine. Some measure of concentration works. We have a second process which is more complicated. a variation on the Chinese restaurant process, yeah?
So is the sample space grown?
In
If
the first place,
an example one.
no.
So
I mean, it's growing like exponentially, but in the usual way. So omega, the local sample space is not growing, it's always the same. But omega t is the product of the omega t's up to t. And this one is always constant. So that would be in the coin case, this would simply be 0, 1.
yeah,
Then omega t would grow like 2 to the power t.
sequence length.
Yeah.
Yeah.
So that is the standard case exponential phase-based growth with size of the, or in this case, length of the time extent of the system. And now we can, however, look at different processes of interest. And one is the so-called Chinese restaurant process, but this is not the case. It's a very simple process with paths, with some sort of memory and path dependence. And it works like the following. You have a infinitely long street, and you have one restaurant after another. And in each restaurant, there's one table that is infinitely long. So you can place infinitely many people on each table. And now customers go through this street one after another. The first customer entering finds the first table empty and sits down. Then the next customer comes and sees, okay, on the first table there's already somebody sitting, and now with probability 1/2 you can choose to sit at this table or go to the next free table and sit there. And the third customer comes, sees, okay, then, and now it depends on what the first customer did. Did the first customer sit at the first table? Because when sitting at the first table, or did he or she go sitting at the second table? So this is basically already this first decision. So in the first case, the first table is occupied. If the second customer also sits at the first table, also only the first table is occupied. If the second customer chooses to sit at the second table, 2 tables are occupied, and then this goes on and on. And all we are saying is that the customers can choose to sit at any of the occupied plus 1 tables, with 1 divided by the number of the respective number. So if 2 tables are occupied, you sit at the first 3 tables with probability 1/3. Good. So this gives you a phase-based growth, which is actually exactly behaving like n factorial. So it's essentially n to the power n. It's a super exponential growth. So instead of like 2 to the power t, it grows like t to the power t. And that is what we see here. We can again choose lambda to be the usual logarithm, and then we can choose, we have to choose g of t to be of that form, which basically means that if you normalize now if you again think of this as being t times the entropy, so if you again now would like, okay, I divide by the number of emitted symbols to get the reduced entropy, you would still have a function that grows logarithmically in t. So your uncertainty about your process, so your process is actually producing more and more entropy as it proceeds.
How would this tie back to the bulk of the number of states concentrating in this region? set A epsilon that we defined?
That simply means the log of the size of the typical set grows like t half log t.
The log of the size of the typical set grows.
Yeah.
So the number of states, the number of paths is growing.
You
Obviously,
have a your yes. So here you see, okay, S of lambda divided by G goes to 1, but also lambda size typical set divided by S goes to 1. That basically means lambda size typical set divided by G goes to 1 asymptotically. And that means now here that log size typical set goes like this. So your phase space grows. First of all, already your phase space omega grows super exponentially, not just exponentially, and also your typical set grows super exponentially. But still it concentrates all the I thought I had one more. Oh, I didn't. I can show you later at the end. I did somehow forget to put it in. One graph where you see how the simulation of the Chinese restaurant where you see how the estimates actually lie on, so the theoretical estimates lie on top of the measured experiments.
so if I may paraphrase, so take, let's say the slogan is the phase space grows really badly.
Yeah.
But if you were to go in and look in the street, it's not as bad as it would appear at first glance. You see a smaller amount of realizations, typically.
Exactly. And your use of typically is exactly why one uses the word typical here, because which basically means if you zoom in and look at really at those paths that relevantly contribute to your statistics, then this will always be only the statistical set, almost always just paths from the typical set. So you can ignore for most, actually for all estimates, as long as your process is simple. You just need to look at the typical set. Right. Okay. So basically, this means that we can measure entropy production of, or at least estimate entropy production of non-IIT systems, so systems with memory and with super exponentially growing phase spaces. Still with the same technology, we can find, if you can find the typical set and can infer how it grows, which is usually doable. I don't say it's always easy, but it's doable. Here, I think it took me 10 days, and in the end, it was 3 or 4 pages of dense calculations, but already cleaned 4 pages. So it was not the shortest and not the easiest thing to do, but it's doable usually, while trying to find a reasonable algorithm that estimates that segments my data stream into useful words and then estimate it like that, like I described yesterday. I'm working on that since 2 years, and the algorithms are still not. I'm still not happy with them. So that's not only a theoretically satisfying, but also a practical thing to have in your pocket. Well, like physicists always do, if we cannot do things exact, we look for measures. And asymptotically, all this becomes exact, so that's not the problem. The problem is more how fast does it converge? So these are hard problems. So how large is the error that you make if your t is still finite? These are still valid questions, and you can tune it here actually by choosing your localizer and adapting your typical set to your problem. That is, so here the non-uniqueness is actually helpful rather than an obstacle.
Right. Yeah. So let's say I was given this Chinese restaurant process, but I didn't know what it was, and I was given samples of this process. I would be able to compute the entropy using this machinery, given a random set of paths, and I would be relatively certain that that would be the actual entropy of the process. So basically, I'm very likely not to be given some super obscure sequence if I just measure this.
Well, if you have enough data and over a long enough time, you could get the curve and you could fit this function. Yeah, you could estimate this g t graphically.
Okay.
And then interpolate a function. There you still have some uncertainty because you have to fit the function where you do not have data up to t infinity. You have t up to some point. Of course, yeah. But at least for this time range, you could make a nice estimate about how your process evolves up to time t, how it would evolve. You maybe then still be comfortable to extrapolate some time to the future, but you know how it is with fitting errors. You probably also make some errors. You would make some errors extrapolating to t infinity, but well, yeah. So this is still better than running into the other complications that one could have using different technologies. The other technology which is quite promising here is the chain rule, which I didn't discuss in detail, but chain rule of so you basically use that if you have p of x t minus 1, that you can rewrite this in terms of p x t conditional of p minus 1 equals 1 times p x t minus 1, and then you can make a telescope expansion, and if you have to take log of this, you get the sum, and if you have some idea on how long your memory range is, for Markov, you just need to the latest observations, but you could make estimates of how long are your typical patterns, and then you can make some average over this. So you could, and this works very well. But so we have this and this, which works very well. And here you even have sometimes the chance to do something analytically, which is also a nice feature.
So if I may return to this, so how is this different from thinking about a normal Boltzmann ensemble, and you're given some sequence?
It's not different. It's not different.
Okay.
The only thing that's different now is that your ensemble is not made up of states, but of entire paths. And if you want to compare to physicists, of course, have already used notions of path entropy. And if you go to ET chains, here,
ET chain.
yeah, yeah.
Oh, it's a person.
It's a person, yeah. Edward Thompson James, I think.
Okay.
Yeah. And he was actually a physicist who worked a lot in imaging. And when you work in imaging, you are confronted a lot with Bayesian methods. And so he was actually spearheading all this maximum entropy philosophy. Basically a philosophy, because it's a philosophy of inference, where you say, well, I always do, I maximize entropy, and what could be is that I do not know all the constraints. So if I make a maximum entropy prediction which is wrong, then this tells me, or tells us that the constraints that I'm using are still incomplete or wrong. The problem is that once you have the constraints in place such that your prediction matches your data, like in most times when it comes to inference, you cannot guarantee that your model is now the truth. All you can say is your model that you have no difference anymore to infer a better model. You still cannot, if you still could be, if you have more data, that you can still resolve some more, and you see, okay, I still have not explained this part of the distribution function, and we may have to add another constraint, but this is simply how you think when you come from the Bayesian side. So every time I get new data, I have the chance to increase the accuracy of our model, to test another hypothesis, and that's about that. Okay, so
I think your battery almost runs out. I think the battery of your laptop.
oops. Thank you. I usually don't always plug it in because I want my battery still to work. Good. Summary, I think we discussed. Good. With that, I think I will close my discussion on generalized entropies. And now, for the rest of the today's session, I will talk a little bit about irreversibility, because that's also a point where I think there's some confusion, and I'm not the first one to notice this. So this type of confusion already also has been discussed by James, which basically comes from the fact that to mistake thermodynamic reversibility with macro-reversibility. So with reversibility of the, so let's say with most of our natural laws are time symmetry invariant. So you can flip time direction, you still get the same laws, which has led to the conclusion, which has led people to believe that thermodynamic processes should actually always be reversible, in that sense there should always be a reversible solution. But this is actually not true, because in that case we mistake macro-reversibility with thermodynamic reversibility, which works a little bit different. And this is cannot. So what I would like to imprint on you is that irreversibility does not happen in the dissipative part of the process. So if you only have heat exchange and whatnot, everything works reversibly because you actually have just the atoms wiggling around and transferring kinetic energy to their neighbors and so forth. Where irreversibly emerges is at mechanical interfaces, and I will now show you how this happens. And I think we could. I'm not sure whether I will fully finish this today, but I will start discussing it, and whatever remains to be discussed, I can continue on. So where does irreversibility and in particular friction come from? So we can make a model. And to show this, we just take a model, the ideal gas as a model. We take massive point particles as our model, and then we demonstrate where does irreversibility come from. And it was quite strange because I really, when I did the calculations, originally, which is gas-kinetic calculations, I said, okay, let's try what happens if we make the gas-kinetic calculations, which actually I remember that the first time I saw them was actually in high school, where because they are so simple, you just take your cube, look how many particles are traveling with average velocities between the walls, look at the times, the average time that elapses between two particles hitting the wall, computing all the momentum transfer, and then you can actually arrive within a few lines of computation at the equation of states for the ideal gas. P times V is nkt, so the classical thing. But in this calculation, the piston doesn't move, just a static volume. And then I said, okay, but let's try what happens if we move the piston at finite time, what changes? And for a long time, I didn't believe that nobody did this, and actually somebody did it. But there were only two works. The one was a paper published in a very obscure American physics journal, because it was American Journal for Physics Didactics. So it was about didactics rather than anything else, where they looked at the elastic collision process between a particle with mass m and a piston with mass m. And this example I also found later in one, but only one statistical physics textbook also from the mid-60s. So this is the only times I've seen that anybody considered, at least peripherally, the moving piston. But one can do it, and one can actually see a few things that are important here. In the end, we will arrive at the thermodynamic uncertainty relation, which basically tells us that the time you take to run through a thermodynamic cycle times the irreversible energy that you lose by doing so is always larger than the action constant. And this action constant, so it's a little bit like in quantum mechanics, where you also have delta T times delta E is larger than H Planck. in this case, our h is not h Planck, it's also an action from the dimension, but it's the particular value of this constant depends on the physical dimensions of the system and are proportional to the number of particles involved and the physical extension. We will come to that later. And good. So that's what I've been saying. So the irreversibility comes if you look at the thermodynamic equations, not from the heat related part, but from the work, always from the work related part. And the second law, if we look at that, this second law would, in the classical formulation, would simply say, okay, if I go, so in the Carnot formulation is if I go through a circular process in my thermodynamic machine, I go through a Carnot cycle in this case, or through a simple compression decompression cycle, then in a closed system, the entropy has to be non-decreasing. So if the circular integral of the entropy is 0, then the process has been reversible. If it's larger than 0, it has been irreversible. Meaning that if the system is isolated, actually by performing a work cycle, the working medium in the system has become hotter. There's more heat now there's more energy now in the system than before the cyclone. So you don't actually come really back. And Planck also looked at this a little bit differently. And he looks again also at the adiabatic work cycle. So the system is isolated in terms of heat, and this is exactly what this means. If the work cycle goes to, if the circular integral around over the work is 0, then the work I put in is exactly equaling to the work I got out. There's no irreversible work lost. And in that case, I've lost energy to the system, and this get moved. Yeah, so that's a different formulation of the second law in terms of work. Here again, a little bit the thing. So we have the adiabatic work cycle. So we have the Carnot work cycle, and if delta W is 0, it's reversible, otherwise it's irreversible. And now we try to figure out, that is also something that we discussed yesterday briefly. Thermodynamic potentials work if things are reversible. So that was always the thing. Why? Because if we go through the PV diagram here and we take some paths in the PV space, and we are reversible, we know that the circular integrals are 0. So it doesn't matter which path I take from some point A to some point B. The difference in value does only depend on the endpoints, and not on how I go there. If we have irreversible contributions, this is no longer the case, and we get a system that becomes path dependent. So the amount of work that we have to invest to go from A to B becomes path dependent. And in this case, which which is why the thermodynamic potential approach typically breaks down for irreversible processes. And that is why when we discussed this generalization of the thermodynamic potentials to non-IND processes, then we are talking about the internal thing. We never looked at the mechanical interface. As long as you don't have a mechanical interface, you don't get this type of irreversibility, and your thermodynamic potential approach still can work because your system remains path independent. But here now we get explicit path dependence, and how this happens now can be actually understood quite easily. If you take a piston, if you take a cylinder, you have gas in the cylinder, and you now want to compress the gas. Then in order to do that in finite time, if you have infinite time, you just hold the pressure, and I have no additional pressure on the piston, then I'm actually not moving the piston at all. In order to move it, I need to actually add a little bit of extra pressure. And I need to add a little bit of extra pressure to push it in. Now I've invested work into the system, and now I want to get it out again. So I'm holding again, but as long as I'm holding the piston, the internal pressure, the piston is not really coming out. So I have to at least reduce the pressure here a little bit so the piston can press out. And exactly this difference between the added pressure I need to push in and the subtracted pressure that I require for the piston to come out, they make up part. They are responsible for the irreversible work that is happening. We can also see it differently. As long as this piston does not really move, I can pretend the piston goes in or goes out, and I'm always looking at the collision between the molecule and the piston in the same frame of reference. So the center of mass system for the collision is identical in that case when I push out or pull in, because I do it infinitely slowly, and actually I don't change my center of mass system at all. However, if my piston is coming out and is passing, and I would like to evaluate it here. Now where piston moves out, then the center of mass system of the piston moving out is different from the center of mass system when you push it in. And this is why microscopically at the piston interface, it is your control over the piston that makes the system irreversible. And in that case, micro-reversibility is not the same as thermodynamic reversibility, because you are actually controlling the piston. Good. That being said, so is now can we conclude these things? And
in this case, that is the case because as a human, you're not very efficient, or
no,
you lose efficient and you lose how do you call it, efficient energy, because you don't if the piston goes out, you don't
you want to perform.
You are not able to change the kinetic energy into usable energy. But if it wouldn't be you that doing it, but a very efficient machine that perhaps could almost have 100% regenerative.
The point is simply that we want the machine to run. We don't, the machine is most efficient if it runs infinitely slowly, because it can sample every fluctuation in the system. So the piston then can sample every fluctuation in the system. But we want to work machines to work at finite time, so we want the piston to move at otherwise we actually have no power output.
Right.
And what we usually want to do is not maximize efficiency, we want to maximize power. And can take my drill and can be very efficient if I put it in a very low gear, but then I also take a lot of time to do it, and that's the same thing. So what is happening is actually that the piston, so one can understand it in the following way, that the piston moving out and the piston moving in see a different velocity distribution. So the velocity distribution of the gas molecules, if you think that the piston, that's always a thing that we say that the piston moves still slowly with respect to the velocity of the gas molecules. So it's not, we don't move the piston at the same order of magnitude, which is a completely fine assumption. So when the gas is basically, we move the piston so slowly that we still can assume the bulk of the gas to be essentially in equilibrium with itself, meaning that the velocity distribution of the gas molecules is still a Maxwell-Boltzmann distribution, but still now the piston moving out sees a little bit a shifted distribution that is shifted by its own velocity. And as we know, if entropy is something like logarithm of probabilities on energy distribution functions, then shifting such a distribution function tells you that also the entropic contributions are changing. This assumption actually allows us to still make these connections. We still measure, say, okay, the average kinetic energy that is let's say the Z component is the component that is orthogonal to the piston surface. Then the kinetic energy with respect to this degree of freedom is the internal energy divided by the numbers of particles divided by the degrees of freedom, equal to 1/2 kBT. So that is the usual temperature definition of equilibrium. And we assume for the bulk of the gas this still works. Then we can replace the average set velocity with this term, or the average momentum of a particle with this term, and the inverse temperature would be as always. However, now we have to see the following. So we now take the piston, we move the piston, and now all the time molecules are bouncing against the piston with a small time interval. We shoot it at it. So what happens is that we accelerate the piston with the force that we press, and between the collisions now we have a constant acceleration of the piston. Then a particle hits due to the collision. The velocity of the piston is instantly made smaller. Again, we can accelerate between particle collisions. So the micro velocity, so the velocity of the piston at the micro level will somehow look like this. And so we can define a macroscopically a macroscopic piston velocity simply by taking here this average, the midpoint of this thing. So we average out the micro jitter of the piston due to collisions. Actually, we assume here that the piston is a rigid body in the sense of Einstein, which however has one could make the critique now that the piston actually itself is a thermodynamic system, and we would have to also compute energetic equilibria between the piston molecules and the molecules in the gas. But to avoid this problem, we just said, okay, the piston is a rigid body, and this jitter is basically a reminder of the fact that the piston itself is a thermodynamic system, because now this jitter is somehow actually corresponding to the temperature of the piston itself. Basically, yeah. So that's was what I was saying. So the center of mass system between for the collision between a piston moving out and moving in is different. And now we can simply use what we know from classical mechanics about elastic collisions to make the following computations. If U bar overline U is the if we go back here briefly, is the velocity directly of the piston directly before the next particle hits, and underline U is the velocity directly after the particle hits the piston, then and the particle moves at velocity vz, then we can of course now compute the piston velocity after the collision given the piston velocity before the collision and the particle velocity before the collision, and we get the particle velocity also after the collision. Then simply now classical mechanics 1, and then we can, that's what we now did. We did derive this, I mean, we didn't derive it here. And now we can put up some equations that are natural. So the velocity directly before the next particle hits is simply the velocity directly after the previous particle hit plus the acceleration that we put on the piston times t. And this acceleration is exactly, oh, I forgot no, that's fine. So that's the force that we have to apply. We have to accelerate actually the piston with this acceleration. So that's the force that we apply. And then we get effective first derivative for the if L is the position of the piston along the z-axis, then this L changes, and then that's what we said before. We take this midpoint, so the average. We take the average velocity during the acceleration phase. So that's that one, and the second, for the second macroscopic derivative of L, we just take the finite difference approximation of the derivative, where delta t is again this intercollision time. Then we can estimate actually the intercollision times, because we know now if you look at all the particles in the range, velocity range between Vz and Vz plus dv, then for this velocity, for particles with these velocities, they will have a set displacement that would be L divided by this dn, but which means that we can compute the collision frequency in the following way. So that's then the formula for the collision frequency. Because what we need is the relative velocity between particle and piston to. So if the piston is running, the particle has to catch up with the piston. So that's why we have here this velocity difference gives us the collision frequency. And when we now say that the particle number around the density, the velocity density is given by this Planck, by the Planck distribution, Gaussian distribution here, then we can actually compute this. That would be the total, the normalization value. That would be the total collision frequency, and this would be the average velocity of particles the piston sees. So if the particle velocity is a Gaussian in the bulk of the gas, then the average velocity of particles colliding with the piston is given by this formula. You start here with at the bottom with L dot, because all particles that go in the other direction or are slower than L dot, they cannot catch up with the piston otherwise. So that's the lower part. Upper part is also clear. The integrals can be explicitly performed. And I already did some approximations here to throw away some terms which are of second order in L divided by the bar, the average set velocity of the gas. And then we can still simplify that because that one can simplify this a little bit. Then we have one correction. Okay. Then if we now put in from the earlier calculations, we know now that the expected inter-collision time delta t is given by this one integral 1 over b 1 over phi from before. Then we can also compute the average distance between particles colliding with the so if we really think of the problem particle, and here the piston, and here we shoot now the particles with here delta z, and the time it takes between collisions would be delta t. So just shoot them in a row onto the piston. And then we get, putting all in, this following equation. So actually we still would have to replace now here this Vz by bar Vz and this delta t with this delta t, and we are actually having the equation of motion. And that relates now in the following way. Okay, that relates now in the following way to the force that is actually acting on the gas. The force that is acting on the gas is now given by this first expression, and this Q is simply a number. This is square root 2 divided by pi. I think it is just a this term is actually responsible then for the irreversibility in our system. And if we now say we can, when this is the force acting on the gas, then we know that the pressure is this force divided by the piston surface. And this allows us now to, if we look back at this equation, this first part here, this first part, so this we can multiply to the other side, and then this mvz square relates to the temperature. So we get now this equation that we have here, that we can rewrite the previous equation into this one, where this delta P is actually exactly this term times this term divided by A. So this is this delta P, and this delta P is always positive. So that's why things become irreversible. This is the internal pressure in the gas, and this is the pressure felt by the piston. This is the internal pressure in the gas, which is simply this part. And the difference, which is this part, is always positive. And so what you have now is that, I mean, this is easy to understand in the sense that if you push in, then the pressure felt on the side walls of the cylinder, that's the internal pressure P, and now here the pressure felt here is P plus delta P. So it's positive, delta P is positive when you are pushing in. That's what I want. That's how you have. So it's so I have to amend this actually. It's not that which is positive, but that times L dot that is positive. So if I push in, L dot is negative. So minus L dot times this is always positive. That's why this term gives you a positive contribution to work whenever you push in or push out, while the other part becomes reversible. And that this is the case that the piston is a higher pressure than the internal pressure of the gas while pushing in. This is something that engineers know. That's well known. And we are, I think I'm almost through. Almost through. I will speed a little bit through it, and then we can maybe discuss in the afternoon a little bit more. Good. Now I can look at the total work that I have to perform. So this would be the work integral, the force I use to accelerate the piston times the path that I take, and then I can, if one does the computation, you actually see that you get one term that is m n dot and 2 dot, which is the classical. This is the, if you would only have a piston with mass m, that's the amount of energy you have to input to accelerate the piston to a velocity L dot. But that part is reversible because you get it out when you deaccelerate the piston again. I mean, it's simply put in the kinetic energy, and in the end, I can still use this energy and take it out again. So that is what then we can split off this one and get a contribution that is solely related to the gas. And then again, you see, okay, you get this part, which reverses under time, under moving in and out. So but this one not. So you get here now L squared. So the sign of L dot doesn't matter anymore. It's always positive, and that's why this now becomes the irreversible contribution, and path-dependent work. And now I will just 2 minutes and in more detail in the afternoon. Then the next thing you can do is you can say, okay, now I have my functional that tells me how much work I have to input if I take a particular path L. Now I can do a variational principle and ask which is the path, the optimal path, which is the path that produces the least irreversible work. And then it turns out that I get this this differential equation with this solution. So this is basically I have to accelerate linearly, basically. So that would be the optimal path that produces the least irreversible work. Funnily enough, that is true for the isothermal case, but it's also true for the adiabatic case. And that is now some image how this irreversibility comes along. I have to, if I push in, while I push in, the piston sees a little bit a higher pressure, and then I pull out, and during pulling out, the piston sees a little bit a lower pressure, and then I get here this part here is basically the amount of work I lose irreversibly for the whole Carnot process. The Carnot process is a little bit complicated because the adiabatic formulas you have to do some little work there, which I don't do here. In the end, in both cases, here and here, you end up with such a formula, so the amount of irreversible work times the cycle time is larger than a process. And what this means is exactly what we say. If we perform very slowly, we have basically no power output, but the machine is incredibly efficient. Then the efficiency would somehow go like that. Oops. Here the efficiency is zero. And so what happens is basically that we have three regimes. We have a maximum efficiency regime. We have a maximum power regime where the machine has a maximum power output, which engineers also know. So if you have a drill and you let the drill work, there's one frequency, where the drill has maximum power output. And then you have one thing here, which is so the system in idle mode. So you take your drill, you don't perform outer work, you just switch it on and then it runs at some speed. And actually all the energy it just uses to run. It does nothing else. It doesn't perform external work. And that's the engine running idly. And there again, the efficiency is zero. You have no power output. You do not perform work. And one could ask now, and we will do this discussion actually on Thursday, that there has been some idea around that biology evolves its biological machines towards a point where they are actually performing maximum power output. And this may be true for macroscopic multicellular life, but it's not true in general. So one knows, for instance, some bacteria living in sea sediment, which almost exist at suspended life. So their cell cycle takes about 1 million years. So the cells live actually multiple million years and only reproduce once every million years. So they work at the maximum efficiency level. So they are in environments which almost have no energy. And so they just are basically waiting in suspended life to gain a little bit of energy, and then they make one cycle, and then they lie still again. So this would be the maximum efficiency range. My cycle time is enormously long. Then we have creatures like us, which perform close to maximum power. We want to compete and whatnot. So that's happening here. And then we have ecosystems and planets, which perform no exterior work and just metabolize solar energy. And they do this here at the idle point. And that's why irreversibility considerations are always quite interesting. So here again, that's how the efficiency drops off towards, here would be the idle point. That's how the ratio between the thermodynamic action constant and H Planck evolves with the cycle time. That's how the optimal Hanel switching positions behave, and that's what I showed before: the reversible work, the reversible work, the irreversible work, and the total power output. I think there's a mistake there. And just for curiosity's sake, we looked at two machines: at the macroscopic machine, which would be something like a big bicycle pump with a cylinder that is 1 meter high, I think, and another machine where we take a piston. We think of a piston which only contains one helium atom and has a diameter. It has a length of 2 classical helium diameters, so a very tiny machine. Think of it as hydrogen bonds with hydrogen bonds we are even close. Yeah, doesn't matter. So if we operate these machines under room temperature and usual external pressure of the normal 1 bar pressure that we have, then for the microscopic machine, we see that, for instance, the action constant for the microscopic machine, for the single atom helium piston, the thermodynamic action constant is basically 5 times larger than the Planck constant. So actually for microscopic machines, the thermodynamic irreversibility is of the same order of magnitude as quantum processes. If you actually reduce it to the size of the hydrogen bond, we even come closer to H Planck. And for the macroscopic machine, however, where are we? 1 meter piston, 10 square centimeters piston surface. We get under normal pressure, we have 5 times 10 to the power 20 helium atoms in such a piston. Then we get the action constant is again something like 5 to the times 10 to the power 10 max Planck. So all I'm saying is if your machine is microscopic, the action constant of the machine is in the magnitude of the quantum action constant. If the machine is macroscopic, also this action constant for these macroscopic machines is of macroscopic dimension. And the maximum power output of this piston would be at a frequency of about 5 5 revolutions per second, so 5 hertz. That would be the maximum power frequency for the macroscopic engine, which is a reasonable number, we believe. I don't have to, if you are performing very fast with a bicycle pump, that's somehow close to what you would get. The frequency for the microscopic machine is interesting because it's 10 to the power minus 10 seconds, and which is in the middle of the microwave range, and which is also reasonable if you think, why do we use microwave? Because it does a maximum, you have maximum energy transfer to the hydrogen bonds. And that's why we can cook with it. And that's also quite reasonable result. So we see the theory not only can be computed, it also produces reasonable numbers. And with this being said, the last thing is that this means that even in classical mechanics, you have a localization problem. So you have a measure in the sense that to gain 1 bit of information about the position of a particle, meaning that you squeeze the possibilities of where a particle can be by half of its volume, so that means you increase your knowledge by 1 bit, is associated with irreversible work. So if you want to know this in finite time, then you actually lose energy, and you have no idea how much energy you transferred in the process to the particle which you are measuring. So so even there you get so the thermodynamic uncertainty relation actually transfers very similar than in the quantum case to uncertainty between the position and the energy state of your measured particle. And all the rest we discuss in our afternoon session. So thanks.
Yeah, thank you.